Okay, we're going to look a bit more about defining functions over lists in this activity, and before we move any further, let's take a look at how we define the maximum of a list of numbers. You had a go at that in the last activity. Let's see what you came up with. Well, here's the template that we saw last time. Maximum of an empty list, we give the answer outright, and we give the answer for maximum x cons x's in terms of maximum x's. Now, what about maximum of the empty list? Well, it's not obvious what that is because there isn't anything there. Now we could give an arbitrary answer like minus infinity or 0 or something like that, but let's instead change the template a little and say, actually, we're only going to give a maximum for non-empty lists. This definition will fail if we put in an empty list, and that's probably reasonable because we've probably made a mistake if we wanted to find the maximum element of an empty list. So, what about a maximum of a list with just one element, that is, the list with just x in it? Well, obviously the answer is x itself. Now, what about the general case? And this non-empty pattern will only match a list with at least two elements, because remember we match patterns sequentially. If the first pattern matches an argument, we'll use that case. So the first case will always match singleton lists, and then the second case will match lists with two or more elements. Now, we want to define maximum of the whole list, x and x's, in terms of maximum of x's. So we've got the maximum of everything but this new element x. So what's the maximum of the new list? Well, there are two answers, aren't there, I guess. It could be the maximum of the tail. It could be x itself. And in fact the answer is it's going to be the bigger of those two. So it's the maximum of those two. So we just apply our binary function max to x and the maximum of x's. And in a similar way, you can do a maximum calculation as a tail recursion. And I'll leave that for you to check if you didn't do it before. Right, the other thing I wanted to talk about before we go on to some more examples is just to remind you of the shapes example. So I wanted to use that to beef up not just to deal with lists of numbers. And remember what we were doing is representing geometric objects like a circle or a rectangle by a tuple. The first element tells you what sort of element it is, first item in the tuple, so it could be the atom circle, could be the atom rectangle, and then it's followed by a pair, tuple with two elements, which represents the centre of either the circle or the rectangle, and then the height and the width in the case of the rectangle, or the radius in case of the circle. And we're assuming that these are rectangles that are aligned with the x and y axes. So they look like the picture there. So this is what our geometric objects look like. And we use pattern matching in defining functions over them. So if we were giving the area, we'd have two cases. One case for a circle, where circle with centre x, y and radius r, the area is math pi times r squared, and in the case of a rectangle with height h and width w, the answer is h times w. So remember, we use pattern matching there to distinguish between the two cases of circles and rectangles, and also to extract components. We extract the radius as r and h and w in the case of the rectangle. So there we use pattern matching. Now what I want to do is do a couple of examples of processing collections of shapes. So suppose I give you a list of shapes. What's the total area of all the shapes in the list? And how do we select just the circles in a list of shapes? I've got a list of shapes, some could be rectangles, some could be circles. I want just the circles. And you can see examples of those two functions here. Now, let's look at the first problem. Suppose we've got this list like this, a circle, a rectangle and a circle. What we have to do is find each of the areas and add them all together. So, the classic strategy for writing a function which gives us a list of, which processes a list, is to use list recursion. We could write down our template and do a direct recursive definition of this total area function. But wait, let's think, again, this is a classic programming strategy. It's not just a strategy for functional programming, but let's see what we already know and see what we can reuse. There's no point in defining everything from scratch. What do we already know? Well, we've already got an area function. So if you have a shape, you can find its area by applying the function area. We've also got a function, that's what we did last time, to give us the sum of a list of numbers. So, what's missing? What we need to do is find out each of the areas. We have to somehow calculate a list which has all the areas of the shapes in it and then sum that list. So here's our total area function. We say apply this function all areas to our list of shapes, put that in the variable all areas and then sum that list. But of course we could write it even more simply as a function composition again. First apply all areas to the shapes, that will give us a list of areas, and then apply sum to the result. So what we need to do in order to define total area is to define this function all areas. And what that does is take a list of shapes and give us back the list of areas that it contains. So there we see our list of shapes. If we apply all areas to it, we get our list of areas, as you can see there. 12.57, 6 and 3.14. So, what do we need to do? Well, the first step is to write down the template. We say what all areas of an empty list is, and we say what all areas of x cons x's is in terms of all areas of the tail x's. So what can we say? Well, we've got a list which has no shapes in it. What's the list of areas of that? It's the empty list. What about the other case? The key step in defining the recursive step is if I tell you that the list, that all areas of a particular list is 3.14, etc., and we stick another list on the front, then all areas of that new list is got to be the area of the first thing added to the front of the existing list. So in other words, what we do is we build a new list whose head is area of x and whose tail is all areas of x's. And this has the effect of applying the area function to every element of the list. And this is an example of what's called a map. And we'll see that that's something that we meet again and again. In fact, we'll spend some time at the beginning of next week looking at how we can define that as a function in its own right. But for the moment, we'll just carry on looking at particular list functions. So here we've got our definition that says, for all areas of the empty list is the empty list, all areas of x cons x's is area x cons all areas x's. It's a new list whose first element is the area of x and whose tail is the all areas of the tail. So that was an example of mapping, of transforming every element of the list. What I want to do in this second and final example is to do some extracting elements from a list. Suppose we've got a list whose first element is a circle, second element a rectangle, third element a circle. What we want to do is build a list whose elements are just circles. And we call this function circles. And you can see I've written out the template again, circles of the empty list, we define outright. Circles of x cons x's, we define in terms of circles of x's. So, what do we do here? Well, if we've got a list with nothing in it, then nothing. There are no circles in there, so the answer is an empty list. What about the general case? Suppose we've got circles of x's. What is circles of x cons x's? Well, it depends on whether that first element x is a circle or not. So we're going to have to change our pattern and say, well, if it is a circle, then we add it to, it becomes the first element of our answer, and the rest is circles of x's. If it's anything else, if it's a rectangle, then it doesn't get included. So it just gets included, we just answer circles of x's. But there is a nicer way of doing this. We just pop back a second. You can see that here we've pattern matched that circle xy, radius r, on the left hand side, and then we've built it up again on the right hand side. So there's an easier way of doing this pattern match, and what we say is this. We say, let's match C, which is a circle pattern. If we match a circle pattern, we put it in the answer. Otherwise, if we match a rectangle pattern, we don't put it in the answer. So in the case that it is a circle, that's the head of the answer, and the tail is circles of x's. That's whatever other circles are in the list. If it's a rectangle, it doesn't get included, so we include just the circles in x's. And that will pick out precisely those elements which are circles. Now, I've used pattern matching here. There's another way again of writing this, which, remember in the earlier activity, we looked at the case statement. What case does is allows us to do a pattern match over any expression. And what I'm doing here is I'm going back to the original template where we have circles applied to x cons x's, and then inside the body I'm doing a case statement. So I'm saying, is x a circle? Call it C. Yes, if it is, that goes into the answer. Otherwise, the answer is circles of x's. So the case statement there is a bit clearer. We say we definitely want to do a case statement depending on what sort of element x is. If it's the sort of element we want, we include it in the answer. If it's not, then we don't include it. So again, this more strictly conforms to the template that we started off with. And what we've seen there is another pattern of recursion. We've seen the idea of, already seen the idea of summing a numerical list. What we're doing there is taking a list and combining all the elements together. We've seen the operation of finding the areas of all the shapes in a list. So we take a list and transform each element in a particular way. And another pattern we've seen is selecting particular kinds of element from elements with a particular property from a list. We call that filtering. So what we've got here is combine, or sometimes called reduce, and the second element is transformation, or what we call map, and finally we see filtering. So we've got these general patterns which have become very important patterns in big data processing. And we'll talk about those, how those are built as functions in themselves in Erlang at the beginning of next week. But for the moment, it's just good to see that we have these very general patterns of computing over lists. The other thing I wanted to say was something about, we talked earlier on about how lists and tuples were both collections of elements in some way. And I wanted to say how lists, just go back to the question of how lists and tuples are different. If we define a function over a list, by recursion over a list, the first thing we do is to try a template like the one we've seen time and time again. So typically what we do with a list is we deconstruct it, or alternatively, we construct it element by element. Whereas in defining a function over a tuple, for example the area function, we deconstruct it, or if you like, construct it all at once. So we have that difference between lists which we deconstruct or construct iteratively, so we get recursion over them, whereas with tuples we just say, well, we've got all these elements, take them all out and deal with them. So tuples are more like objects, lists are more like collections in an OO world. A few examples that we're going to, you could think about if you wanted to think about some others. That we're going to come to nub in the next section, in fact. But also you could think about, if I give you a list of numbers, tell me what the median is, or tell me what the mode is. Other exercises you could think about. So that's it for this session. We've done a number of different sorts of definitions of functions over lists. What we're going to do in the next section of the course is I'll do some live coding and try and show you some high-level strategies for defining functions, taking the example of list processing as the starting point. Okay, a few more exercises for you to look at now, but that's it for this presentation.